The next generation of radar, detecting microdebris for safer LEO. As an expert in the space sector, I've witnessed the growing congestion in low Earth orbit, LEO, and the increasing threat of orbital debris. With over 10,000 active satellites and millions of smaller fragments, the risk of collision is soaring. Even tiny particles, no larger than a grain of sand, can cause catastrophic damage to billion-dollar missions, disrupt global communications, endanger astronauts, and threaten the long-term sustainability of space operations. It's time to address this issue head-on. The space industry must transition from ground-based tracking to orbit-based detection systems capable of identifying debris at the sub-centimeter scale. This shift is made possible by mmWave radar technology. The invisible threat, detecting microdebris in LEO. Current ground-based systems struggle to track debris smaller than 10 centimeters, leaving these particles as an invisible threat. Mission planners operate with incomplete data and limited collision avoidance options. We need better detection capabilities and more accurate debris models. Orbit-based detection systems with millimeter-scale resolution are essential, requiring a transition from passive tracking to active, satellite-mounted radar systems for continuous scanning in high-density orbital regions. Technologies like rendezvous and proximity operations, RPO, radar and mmWave, mmWave, radar are crucial for understanding and managing growing risks. RPO radar enables spacecraft to detect and track objects during close approaches, vital for docking, servicing, and collision avoidance. mmWave radar, operating at high frequencies, 30 to 300 GHz, provides the resolution needed to detect debris at the millimeter scale while maintaining compact size and low power consumption. At Plextek, we've developed systems specifically tailored to this challenge. The key shift is moving debris monitoring from ground-based observatories to orbit itself. By placing compact radar systems aboard satellites, detection becomes continuous and occurs at the scale of collisions. Instead of extrapolating trajectories from distant observations, orbit-based systems offer real-time scanning of the immediate environment, detecting particles as small as 1 millimeter within the satellite's operational region. Matching momentum in the North American market. The United States is witnessing growing momentum with NASA's heavy investment in space situational awareness and debris mitigation, and the U.S. Space Force prioritizing domain awareness capabilities. The demand for precise, space-based tracking solutions is significant, as current infrastructure lacks sub-millimeter resolution. Major firms like SpaceX, Amazon's Project Kuiper, and Telesad's Lightspeed are facing increasing regulatory scrutiny over orbital congestion, making real-time debris awareness a necessity. The new era of debris detection. Plextek's integrated mmWave radar system offers agencies the ability to detect sub-millimeter debris, marking a breakthrough in monitoring even the smallest fragments. Unlike traditional ground-based tracking, mmWave systems provide high-frequency, non-impact sensing as a compact satellite payload. Continuous scanning within a defined beamwidth allows for real-time debris identification, enabling operators to map high-density debris fields, adjust orbital trajectories, and refine shielding strategies and predictive debris models. This directly enhances collision risk modeling, adaptive shielding designs, and space traffic management strategies, aligning with initiatives like the ESA Zero Debris Initiative. mmWave technology can run on lightweight, low-power payloads, allowing for flexible integration into satellites as dedicated modules or part of multi-mission platforms. Plextek's mmWave radar is one of the first compact, satellite-mounted systems designed for sub-millimeter debris detection at the scale required for operational LEO missions. While other space-based radar systems exist for larger object tracking, achieving millimeter-scale resolution in a low SWAP payload configuration is a significant technical advancement. By implementing this technology, agencies improve detection at the smallest scale, enabling more effective mitigation strategies and ensuring that avoidance strategies, shielding designs, and debris removal efforts are based on accurate, real-time data. Continuous mapping of debris fields allows operators to take a proactive approach to space traffic control, reducing collision risks through precise forecasting and early intervention. Conclusion: bringing new space technologies to market is complex, requiring rigorous testing to ensure systems can withstand extreme conditions. Plextek, for instance, considers radiation hardening measures, robust power regulation, and compact, lightweight designs for long-term functionality in orbit. Implementation responsibility should be shared across the space ecosystem, with satellite operators and constellation providers integrating debris detection as a standard payload requirement, and regulatory bodies establishing frameworks that incentivize or mandate situational awareness capabilities. As orbital environments become more crowded and unpredictable, the shift toward precise, cost-effective, real-time debris monitoring is not just logical but inevitable. A radar system capable of detecting and analyzing debris at this scale is fundamental to refining mission planning, improving spacecraft protection, and enabling active debris mitigation. In essence, sustainable access to space depends on our ability to detect and respond to the smallest threats before they become mission-critical.